In this lesson, we will be discussing functions, domain, and range. So we've already studied functions a bit, and we know that f of x can replace y in functions. We also know that if a number replaces x, it has to replace every x in the equation. So in this example, we have function f of x, and it's equal to negative 3x squared plus 4, and we're being asked to find f of 2. What this means is that everywhere we see x, we're going to plug in 2. So as you can see, my substitution of 2 in the equation is in red. And when I substituted 2 and I put parentheses around it in the equation, this is particularly important if the number that you're substituting is negative. And basically, we get an output of negative 8. So the benefit of this format is that I can clearly see that when I put positive 2 into this function, negative 8 was the result. So while that notation is very useful and very commonly used by mathematicians and teachers and students, there is a more precise notation that people sometimes prefer to use. The argument is that f of x doesn't really define a function itself. It's technically defining an output rather than the function. So in this way, the function is being defined. So here's how we would read this. M is the function which turns any input number x in the domain into the output function, x times the quantity x minus 4. Very long notation. But you can see with the colon that you're talking clearly about function m. The x appears before the arrow, and that tells you that that's your input. So a little more concise. And just one other thing to note, you're going to note that this arrow has a blunt end rather than just a straight arrow, which we've used in the past. So the first arrow, right, basically looks at, like the arrow used in this notation basically says it's defining a relationship between the input and output. And the other arrow, this one right here, in math means tends to. So we're always going to be using this arrow here when we're writing this notation. Let's do a practice problem. If you know how to do this, go ahead and pause it and then check back for the answer. If you don't, I'll walk you through it. So if function g, g is the function which turns any input x in the domain into the output x cubed minus x squared. What is g of negative 2? So essentially, this is asking the same thing that we've always asked in function notation. If x is negative 2, what's our output? So I'm turning this into, I'm basically doing a whole bunch of substitutions. Everywhere I see x, I'm putting in negative 2. And I'm putting those negative 2's in parentheses because they're being raised to powers. And you can see that when I simplify this, I end up with g of negative 2 equals negative 12. All right, now composite functions. So basically, composite functions, or oftentimes they're called compositions of functions, they basically embed functions in one another. So the big rule of thumb here is you always work from the inside function to the outside function. So here's the notation. This is read as f of g of x. So this is one of those notations in math that contradicts a lot of the other things we know. So f and g are not being multiplied. This notation is to say that you're going to embed g of x into f of x. So if you think of deal with g first and then deal with f, that'll help. This is one of the cases where the British notation, which is what you're seeing now, varies slightly from the American notation, which looks like this. So in the American notation, they just use an extra set of parentheses. Both of these notations are equivalent. It's just a matter of preference. So let's do a practice problem. If we let function m, given its input of x, into the domain with the output number of 3x minus 2, and we have function n, whose output is 2x times the quantity x minus 1 for the input number of x, we are going to be finding n of m of x. So remember, we start with the inside and we work to the outside. So if you remember how to do this, you can pause and check back for your answer. So you can see my substitutions. I'm basically embedding m inside of n. So everywhere in equation n that I see x, I'm putting in function m's output, which is 3x minus 2. So you can see that in red. And then I'm just going to simplify this to get this into a nicer form. So you can kind of see that I simplified the far right parenthesis first. And then I'm just going to distribute or FOIL to get my most simplified answer for n of m of x. Here's example C. We have function j, we have function k. This time we're being asked to find function j of k of -1. So we're actually going to be substituting for x. So there are two approaches in solving problems like this. The first is to do what we did on the other problem, where we basically deal with the composition first. We embed function k into function j. The second way to do this is to find k of -1 and then find j of whatever k of -1 is. So we're going to look at both. So here's the method where you perform the composition first. So you can see right here that I substituted function k's output, x cubed plus 8, into function j. So everywhere I saw x, I plugged in x cubed plus 8, it's still squared plus 5. So there's my composition, and now I'm doing my substitution of -1 in for every x. So this sure beats having to distribute x cubed plus 8, right, times itself before we plug in -1. So don't go through all that algebra, you can just do substitution here. And then I end up with 54 as the answer. So essentially, when I plugged in -1 into this composition of j of k, I get 54 out. The other way to do this is to find k of -1 first. So in this k function, I'm plugging in -1 everywhere I see x. So I get a value of k of -1 equaling 7. So now, since k of -1 equals 7, I go ahead and in this j of k right here, I substitute 7 for k of -1 since they're equivalent. And then I just go ahead and find j of 7. And when I do this, I get 54. Now to show that I've composed those two functions, I'm rewriting my final answer just like I did the first time as j of k of -1 equals 54. Moving on to domain and range. We've talked about this in the past. I'm going to do a very quick overview. Domain is all possible x values. The natural domain, which is specific to Cambridge, and it may be used in other math classes, I just haven't used it. Oh, I can't remember if I've ever used it. It's the set of numbers for which a function has meaning. Most of the time, people just call this the domain. Cambridge specifically calls it the natural domain. So if you're trying to put -1 into the square root of x, your calculator spits out an error. That's because when you try to input -1 in for x, it's not part of the natural domain of the square root of x. And we'll explore that a little more. The range is all possible y values given the domain. And then there are some common symbols I just want to review as we are looking at domain and range. So this sideways E, and it's an E, it looks like an E because it stands for elements in many definitions. You can think of it as belongs to. So if there's an X with the symbol next to it, it means X belongs to, or X is an element of. All right, and then this R we've seen many times, we've written it many times, so ours probably doesn't look quite as fancy. It means the set of all real numbers. All right, so let's practice finding the natural domain and range. We're given X. So if the input number is X and the output is the square root of X, where X is an element or belongs to the set of all real numbers, find the natural domain and range. So there's a couple of approaches. If you think about the square root of X, we know, because we've done this many times, we can only put 0 or positive numbers in for X. If you weren't sure about that, you could try to sketch a graph, but sometimes domain comes down to knowing functions. So in this case, what we know is that since our input has to be greater than or equal to X, that's also our domain. Thinking about that, if we plug in 0 or any number greater than 0 for X, what does our output become? So if we think about it, if we plug 0 in for the square root of X, we get out 0. If I plug in 100 for X in this, I get out 10. And I could just keep going, and I know what this graph looks like, as should you, since we've used it a lot this year. That means that our range is Y is greater than or equal to 0 as well. And you could use some software like Desmos if you can't quite remember what something looks like. But here's the graph of the square root of X. And I just went from 0 to a little greater than 8 because I could not put, I didn't want to use a tremendous amount of space. So you can see that it just is on an upward slant, so to speak. So, you know, as X gets bigger, Y is also getting bigger, and both approach positive infinity. This one's a little trickier. So we're finding the natural domain and range of sine of X, given that X belongs to the set of all real numbers. If you think about the natural domain, one of the things you can ask yourself is there any value that X cannot be? And you'll notice that we're in degrees here, so every input for X is going to be a degree. Hopefully you remember from our trig unit that X can take on any value, which means that the domain of sine of X is all real numbers, so it can be anything, or negative infinity is, or X is greater than negative infinity, but less than positive infinity. Either of those would be fine. This is where it gets tricky though. If you think back to sine, while the domain can be any X value, the range has a limitation because the maximum value of sine of X is 1, and the minimum value is -1, which means that our range is from -1 to +1, inclusive of both. So here's just a quick review of part of the graph of the sine wave. You can see that, you know, our lowest point in this whole thing, in this oscillating pattern, is -1, and the highest point is +1. So that's another way that you could look at range. Sometimes we're asked to find a range when we've been given a function, in this case g, with a restricted domain. And what I mean by that is cosine of x goes on infinitely, but we're only looking at it from 0 to 90 degrees. Because of this fact, we also have a restricted range. Like, our range is based on our domain. So the only range values we can find are those associated with the domain of 0 to 90 degrees. I think it's also important to note that it's not inclusive of 0 degrees and it's not inclusive of 90. So if we think about it with cosine, we know it's like, we call it our valley graph, right? It starts when cosine of 0 has a y value of 1, and then it travels down into the valley until it reaches 180 degrees, in which case the y value is -1. Well, the question is, what is the value at 90 degrees? And hopefully you remember that it goes from 1 at 0 degrees to 0 at 90 degrees. All right, so since we're not including 0 and 90 degrees, our range has to be y is greater than 0, but less than +1. because it's not inclusive of those. Now, if you're stuck on this and you need to see a picture, you could look at the graph. And if you put this into Desmos, you're going to get a huge graph, right, that goes infinitely. We're interested in looking at the value at 0, the value at 90 degrees, and what happens in between. And you can see that all of the values in between 0 and 90 degrees fall within our range. So that's another strategy for figuring out what the range is, would be to look at the graph. So as your final thought, your final task, I want you to answer these questions at the bottom of your notes. What were you supposed to learn during this video? It doesn't need to be a paragraph, it can just be some bullet points. And then what questions do you have, or what clarifications do you need in class? All right, and that is our lesson on functions, domain, and range.